Welcome everyone. In this video lecture, we will draw the CMOS inverter layout design using Lambda based design. Okay. So first of all, we have to know about the CMOS inverter. So I think we all are very familiar with the CMOS inverter. So the first thing is our CMOS inverter. So in CMOS inverter consists of a PMOS and NMOS. Okay. So this one is our PMOS and this one is our NMOS, where the gate of each PMOS and NMOS connected together with input, and we are taking output across this side. So this one is our drain of P and this one is drain of N, and source one is connected to the source of P is connected to the VDD, and this one is our source of NMOS. Okay, and we are taking the output across this P output side, and the corresponding cross-sectional view we can say the diagram for a p-type substrate. In a p-type substrate, we have to make a n-well for the PMOS fabrication, and we have to make p plus region and two n plus region in the p-type substrate for the nmos. Okay, so we are familiar, that's why, but we have to know the basics. Okay, and then after this n plus, it is nothing but simply the source terminal. Okay, source of n, and this one is the gate of n, and this one is nothing but simply drain of n, and drain of this end is connected to the drain of P. Okay, and this one is our gate of P, and this one is our source of P. So I have made this one, so I am not focusing too much on this one. Okay, then after what we have to do, we have to draw the layout design. So first of all, we have to think about the NMOS and PMOS. So the very first thing for any layout design, so this one is our CMOS inverter. So we have to make PMOS region and NMOS region. So for PMOS region, what I am doing for the PMOS, this one is PMOS. We have to make a P well. Okay, so it will better to take P well. So I am saying this one is our P well. Okay, a square, sorry, rectangular. Better to say rectangular thing. Okay, and this one is nothing but simply a P well. Right. Okay, and then after we have to make an active area. Okay, and the active area determine the minimum diffusion contact, okay, which is necessary for the source and drain region. So active area we have to also make in this one. I'm saying this one is our active area, or this one is the active area, we can say. Okay, clear. And then after this active area, okay, I am writing the name also, otherwise this one is our n-well or a small n-well, we can write. Okay, and this one is our active area. We are doing for the PMOS first. Okay, one rectangular shape. Okay, then after this active area, width of this active area is determined for the minimum diffusion contact size for the source and drain formation. Okay, and then after we have to make a polysilicon line or metal line. We can polysilicon line, better to say polysilicon line. Okay, and this will give the what get terminal. Okay, so once again I am writing the name polysilicon line. Okay, so this polysilicon is generally we will use for the get terminal formation. So this is for the PMOS. Okay, one n-well rectangular space, then after active area for the P plus region. So this will, if I am saying this one is our gate in, so this either side will be source or drain region, or drain or source region, any one. Okay, we will discuss. Okay, and inside this we can make some contact. Okay, we can make some contact. Okay, we will discuss later, means I am writing this as a contact or something. Okay, so this one I am saying contact. Okay, so for PMOS, this one is our contact. So this thing is our gate terminal, source, drain, source or drain, drain and source, or we will use some contact for the uh, VDD supply, and we have to contact is used to make the supply region and all these things. Okay, clear? So this one is our PMOS, PMOS. Okay, we can say this one is our PMOS. Okay, in our stick diagram, lambda based design, there is this dimension in terms of lambda. So we will discuss lambda, means what should be the value, like for this one, it should be 2 lambda. Okay, this should length will be this width, we can say 2 lambda. This should be our minimum spacing will be 10 lambda. Okay, that we will. So but first focus on this one, means if PMOS, one annual rectangular block, then after some active area for the, this active width will be responsible for the source and drain region, and in between there is a gate one. Okay, now again, so this one for the PMOS. Okay, now for the NMOS fabrication, NMOS draw. If you want to draw, no need to take the annual region. Entire page is we can say the P type one. So just make a active area. Okay, for the source and drain region, and then after, okay, and if you want to make some contact, this one is our NMOS. NMOS. Okay, this one is a polysilicon line. Polysilicon. Okay, for the gate terminal, and this may be our drain and source or drain, anything. Okay, and this one is our contact. I will show you where we have to use the contact and all. Okay. Okay. So this one is our NMOS. Okay, and above one is our PMOS. In NMOS, one active area. Okay, and then after this one is the representation. Okay, one can also this has this line with the polysilicon one. So now this, if someone say what is the active width, or we can say better to say this length. Okay, this length. Okay, minimum, we can say the minimum over all length of this active area. So I am writing here minimum. Okay, length of the active area. Okay, so this minimum length. Okay, I am saying this as a, for example, L. Okay, this length is a L. Okay, so this area will be nothing but simply this separation. Okay, this separation. Okay, say I am saying this one is A, this separation I am saying and this separation I am saying B, and this one is C. Okay, and this separation I am saying anything you can say like D. Okay, so the minimum L value will be D. This polysilicon width. Okay, I will write here. So this D will be this one. So this D is nothing but simply minimum polysilicon width. Okay, minimum polysilicon width. That is our D. The overall length L will be D plus, we can write as twice times of A plus B plus C. D plus twice times of this one is D, and now this length will be same as that of this. So A plus B plus C into 2. Okay, so D is the minimum polysilicon width, and A, this A we can say as minimum separation. You can say the minimum separation from contact to polysilicon edge, from contact to polysilicon edge, or we can say minimum separation from the polysilicon edge to contact. Okay, this one is our A, minimum polysilicon separation, minimum separation from polysilicon edge to this contact. Okay, now what is B? So B is the contact size. B is the minimum contact size. Okay, and what is C? One more thing is there, C. So this C will be the minimum spacing from contact to active edge. We can write as minimum spacing from contact to active edge. Okay, so this one is our minimum separation from the contact to this active edge. So this one is our NMOS, PMOS. Okay, so if you know this diagram, now it will be very easy to draw the uh, complete layout design. Okay, so this one is the minimum length of the active area. Okay, so now we have already made this one. Okay, so now we have to draw the inverter layout. Okay, okay, so I'm just taking this diagram here. Now we will draw the complete diagram for this CMOS inverter. Okay, so the very first thing, if you want to make the PMOS, we want a what? Some active area and well. Okay, then we have to make the contact and polysilicon. So in this one, first we are just making the, suppose this one we have selected the anvil region. Okay, inside that anvil we are making a, okay, active area. Okay, and then after we have to make polysilicon. So but before that I am just making one more active area for the NMOS. Okay, clear, or make it slightly larger. Okay. Then after we have to draw a polysilicon gate line. Okay. Or I'm just drawing a slightly smaller figure to make it more convenient. Okay. Wait. Means first of all we have to take the black color and then draw a P well, N well, sorry, N well. Then inside that we try to make a active area. Okay. Then one more active area for the NMOS and then try to make a for gate one we need a polysilicon line. So this one is a polysilicon line. Okay. Then after we have to just I'm just writing this one first. This one for the gate terminal. Okay. So first make it H line. Make it okay. Then this gate is connected to some input. Okay. So for that purpose I'm just taking a metal. Okay. Okay. For input we are just making like this and we are making a contact. Okay. To polysilicon and metal connection we are putting some uh, contact. Okay. So this is our contact for the okay, and this one is nothing but simply our input, so better to write V in. Okay, I'm selecting different color V in. Okay, and then this is our say gate in, gate kind of thing. Then it should be our say source source in. So this one I is saying it should be this active area should be drain side, and this drain is connected to the PMOS drain region. So this one is also drain we can say, and this one is source of NMOS. So I'm writing a D of N, source of N. This one is line. Before that it may be source or drain, source or drain. So this one is for source of P, drain of P. Okay. So then after we have to connect the drain one with the V output. Okay. So you have to just take the metal. Okay. Okay. This one is our metal kind of thing. Okay, and you have to make it some contact. Okay, so we are making the contact, and this one is for the output. Okay, so we can simply write this as a V output. Okay, drain one is connected. Now one more thing, the source of NMOS is connected to ground. Okay, so make it one metal. Okay, this one is our source one is connected to. Okay, so one more contact will be there. Okay, this one for the ground. Okay, now what we have to do, we have to output is there, input is there. Okay, now VDD, so VDD is there, substrate is also connected to VDD. One can directly make it like this VDD. Okay, so okay, let me take a rectangle. N1 contact, and this one is our VDD. Okay, so this one the source is VDD. So this one is the representation for the CMOS inverter. Very simple. First, you have to make the this annual region. Then this one is our active area. Active area. In active area, we have to make source and drain region, and then this gate is connected. So gate is there. Okay, V in. Okay, so metal. Then output, V output, source, and this one is source is ground and source is okay, clear. And if we have to connect with the this and well also we can give the VDD, but I have just made the simple representation. So this is all about the CMOS inverter layout design. Okay, so thank you for watching this video. Thank you.